The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Well, last time, under the tutelage of Professor Buendy, you started to see some of the consequences, the more immediate consequences of some of the properties we've been discussing over the last few lectures of binary liquid mixtures. And in particular, he started showing you some of the colligative properties by which you see changes in the vapor pressure and the boiling point and so forth that arise because you've got liquids in mixtures, and this affects their chemical potentials. And today I want to start by going through the fourth colligative property that's commonly seen, what's called osmotic pressure. And I mentioned this before. Today we'll go through a quantitative calculation of its effects. And then we'll start in on a different unit of the course. We'll start in on statistical mechanics. So let's continue with the colligative properties. And osmotic pressure plays a super important role, certainly in all of biology, because, of course, inside biological cells you have solutions. Water is in there along with a whole bunch of other components. And so the chemical potential of the water is strongly affected by all the other constituents. And this has profound effects on what's involved in maintaining an equilibrium between what goes on inside and outside of the cell. And this is the case in all organisms, and it's also exploited, of course, in all sorts of other contexts. So what's happening with osmotic pressure is you've got some situation where there's a semi-permeable membrane. It allows one of the constituents but not others to pass through. And typically that's water, although, of course, it could be anything. So in the lab, the way this typically looks is something like this. Here's your semi-permeable membrane. Outside, we can imagine that there's pure liquid A, could be water, could be something else. Inside, you've got A mixed with B, one or more other constituents. And then there's some level of the liquid outside the container. Of course, A can pass through the membrane. And so what ends up happening is, if you just look at the situation, what you immediately notice is that the liquid in here goes up higher than the liquid around it, right? It's at a higher level. It seems counterintuitive at first, and in fact, it can be enormously higher. But that's what happens, right? So there's this extra height, h, of liquid inside the container relative to what's outside it. Okay? And what that means is the pressure inside here must be higher, right? Of course, the weight of this liquid is pushing down on what's down here, right? So the pressure inside here is higher than the pressure outside. But of course, from what you know already about liquid mixtures, this should in fact make sense, because what's happening is that if these things are at the same pressure, you know that the chemical potential of A is going to be lower in the mixture. It's always lower in the mixture than it is in pure A. So there's nothing to stop A from rushing in. So A does rush in. The liquid level goes up. It raises the pressure down here. But as the pressure rises, now the chemical potential changes and goes up. So eventually equilibrium is reestablished, because these aren't at the same pressure. The additional pressure means the chemical potential of A goes up. Of course, it goes down by virtue of being in the mixture, and those two things will eventually reach an equilibrium where the chemical potential of A is the same everywhere as it has to be. Okay? So what we'll calculate now is Okay, how much does the pressure go up when that happens, right? So let's take a look, right? And so, of course, there are all kinds of examples. In typical 1A would be water, and B would be one or more sugars, all sorts of other potential constituents also. Okay, so let's just consider the pressure at two places that are the same level, the same height. We'll label this one point alpha. Let's put some color in here. We'll have points alpha and beta. And we'll make this distance L. Okay? So now let's just first calculate what the pressure is at both points. It's going to be higher here because of this additional liquid on top. So if we look at point alpha, well, let's start at point beta. Actually, that's the simpler one since it doesn't have the additional liquid. And first of all, there's just atmospheric pressure, right? So there's an external pressure. Certainly, typically, it would just be atmospheric pressure. It's pushing down here. It's also there, right? So that has to factor in. So there's our external pressure. And then there's the product of this height times the density of the solution times the gravitational force constant. Okay, and I'll work through that momentarily so you see that that indeed is the pressure that's exerted by the amount of liquid that's up above this level. Okay, but before I do that, let's put the pressure at point alpha. So P alpha, and that's P external plus L rho G. But now there's this additional height on top of that, right? So there's also H rho G. There's an extra pressure, right? We'll label this pi. So we can write P alpha is equal to P beta plus H rho G, which we'll say is equal to P beta plus pi. All right? Now, just to make sure we're all on the same page about these quantities being the pressure that's exerted by the liquid, let's just look at that. So L times rho times G, right? It should be a pressure which is a force per unit area. And in particular, this is going to be a weight per unit area. Remember, the weight is the force that a mass exerts, right? And it's exerted because of the gravitational constant. So what happens? Well, this is just length. Rho is a density, right? So it's mass per unit volume, right? And of course, G is just our gravitational force constant, so it'll be in units of meters per second squared, right? So what's going to happen? If we multiply L times rho together, This is units of length. This is units of volume. What we're going to get then is mass per unit area, right? And that's what it is, of course. It's distributing across the area of that surface where point alpha is, right? So these two together, L times rho, give us mass per unit area, right? So it could be in units of kilograms per unit area per meter squared, right? And now we're going to multiply that by the gravitational force constant. So now we're going to have all together kilograms per meter second squared, right? In other words, it's force per unit area, right? Wait a minute. Is this correct? Yeah. Okay. And so that's what we have. And now, of course, we have the additional component due to the height here, right? Okay. Now, what do we know about the chemical potential in both parts? The chemical potential has to be equal outside and inside the container, right? So mu A at point alpha is just mu A of the liquid at pressure P plus pi and temperature T. And that has to be equal to mu A at point beta, but point beta is just in the pure liquid. So that's just mu A star of the liquid at pressure P and temperature T. Okay? So here's the chemical potential at point beta. Here it is at point alpha. Those two have to be equal to each other. And now we're just going to use Raoult's law. And what does that tell us? We have RT log of XA plus mu A star of the liquid at pressure P plus pi and T. So there's our chemical potential inside the container. And that's equal to mu A star of the pure liquid at point beta, all right? And so we can just rewrite this as RT log XA plus mu A star liquid at pressure P plus pi of T minus mu A star at pressure P is equal to 0. Okay. Now we need the pressure dependence of the chemical potential, right? But we certainly have an expression for that. So we know that dG is S dt plus V dP. The temperature is the same on both sides, but we need to worry about what happens at different pressures. So at constant T, dG is VdP. So now if we look at the chemical potential, which is just the Gibbs free energy per mole, then d mu A star is VA star molar dP, right? In other words, the difference in the chemical potential as this changes as a function of pressure is going to be given by the molar volume of A under these conditions in the pure liquid, dP. It's just the potential, the pressure dependence of G. It's not the kind of topic I would have thought would drive away a lot of people, but you never know. Okay. For the rest of you who are willing to bear with me, let's continue. All right. So now let's just integrate, right? We need to know the change in mu A at a finite jump in pressure from inside to outside the container, right? So we're just going to integrate. So if I want mu A star at pressure P plus pi minus mu A star at pressure P, then I just have to integrate from P to P plus pi VA bar star dP. And now I'm going to assume, and this is certainly a safe assumption, that this quantity, this molar volume, isn't going to change. In other words, the molar volume of liquid A isn't going to change significantly going from the pressure out here to the pressure in here. It's on the grand scale of things, it's a small pressure change. We can assume that the liquid is incompressible over that small pressure change, which means that this is constant, and so all we have then is simply VA bar star times pi, right? So then, substituting back here, right? So now we've calculated this difference. It's a simple result. So then we simply have that RT log XA plus VA bar star pi is equal to 0. Okay. Now, you saw last time, and I'll work through this quickly again, that the log of XA can be written approximately as minus NB over NA. If you remember, this came from writing that this is equal to the log of 1 minus XB. But we're assuming, that B is the minor constituent here. So XB is a small number, right? So that this is roughly equal to minus XB. And that's just minus NB over NA plus NB. And since NB is much smaller than NA, this is approximately equal to minus NB over NA. Okay, so we're going to make this substitution. Also, this quantity, this molar volume of A at the, over the pure liquid, since the concentration of B is low, we can assume that this is just the molar volume of A in general. So in other words, we can write VA bar star. We can just write it as VA bar. That is, we're not going to worry about changes in the molar volume, either as a function of pressure or a function of concentration at the low concentrations that we're working. And then note that NA times VA per mole is just the total volume. Oops, not bar, not the molar quantity. This is the molar quantity multiplied by the number of moles, right? So it just gives us VA, the total volume occupied by A. All right, and using these two results, then we have that RT times negative NB over NA, that's this result, plus VA over NA times pi is equal to 0. NA will cancel. And finally, since almost all the volume is due to A, again because B is the minor constituent, we can approximate further that VA is approximately equal to V. All right? So finally, getting rid of the NA on the denominators, we're left with a simple expression. Pi times V is RT NB. Okay? So we have a very simple expression, which is called the Vant-Hoff equation and expression, and look at how it resembles the ideal gas law, right? This is a pressure times a volume equals a number of moles times RT. Of course, really, it's a change in pressure, and this number of moles is the number of moles of a gas constituent in a solution, right? But it has the same form that you're familiar with. Okay? We also, sometimes it's convenient to substitute, since NB over V, that's just the concentration, right? That's the number of moles over the volume. And in that case, the expression is rewritten as pi is RT times C, where it's understood that this is the concentration of the solute. Right? Okay. Any questions? All right. Let's work through a numerical problem. You know, these things can seem a little bit, they can seem simple, but sometimes when confronted with a problem, sometimes it may seem less than obvious what to do, and also the results can seem a little bit surprising. So I just want to work through a simple numerical example to see how these play out. So let's imagine we have 10 grams of unknown solid dissolved in 1,000 grams of water. Okay? The vapor pressure is 25.195 torr at 27 degrees C. And the pure water vapor pressure is 25.000, no, 0.200 torr at the same temperature. Okay? So first, let's just calculate the molecular weight of the solid. Now this you I think saw from last time, so this is straightforward. It's going to come from the vapor pressure lowering, not from the osmotic pressure, which we'll do next. Right? So the delta P of H2O is minus XB times P star of H2O, right? This is from last time. The expression for the vapor pressure reduction due to the concentration of the mole fraction of B, right? And XB is 0.005 torr over 25.2 torr, right? And that's 1.98 times 10 to the minus 4, so that's our mole fraction of B, right? And then XB is NB over NA plus NB. So now we have this, it's 10 grams divided by the molecular weight, which is in grams per mole, over 1,000 grams of water divided by 18 grams per mole plus 10 grams divided by the molecular weight in grams per mole. But since the solution is overwhelmingly water, we can get rid of this term and make the math simple. Can you see that? I guess barely. Well, so this turns out to be this is our 1.98 times 10 to the minus 4. And if we solve for molecular weight, then we wind up with 907 grams per mole. Okay, so that's using one of the colligative properties that you saw last time. Now let's, though, finish up by calculating the additional pressure that we'll find. So what's the osmotic pressure of the solution? So now we're going to assume that we have that solution inside in a situation like this where there's pure water outside that can go in, and there's going to be excess pressure because of the water rushing into the solution. So what happens? Right? And let's use a value of the density, 0.995 grams per centimeters cubed. Okay? So pi is RT times C. That's 0.08314 bar per Kelvin mole times 300 K times C. C is NB over V, so it's 10 grams divided by 907 grams per mole over 10 grams over 0.995 grams per milliliter. I'm equating with centimeter cubed. And that turns out to be 1.09 times 10 to the minus fifth mole per milliliter. Let's get that into liters. So we'll multiply by 1,000 milliliters per liter. So it's 1.09 times 10 to the fifth moles per liter. Okay? Yeah. Let's see. Don't forget that, right? Ah, yes, yes, yes. And I think that's the case in the notes also. Yeah. Yep. Thank you. Okay. So the concentration, just to calibrate us here, it's a pretty low concentration, right? It's about 10 to the minus 5 moles per liter. The excess pressure is 0.27 bar. In other words, it's about a quarter of an atmosphere. Uh-oh, what's happening?
-1.
Where are we? Sorry. Where exactly?
1.09 times 10 to the minus 5 times 1 by
Or it's either 10 to the minus 8 or 10 to the minus 2. One of them.
Oh, yes. Yes, sorry. Yeah. 10 to the minus 2 mole per liter. Yes. All right. And so the pressure that results is a modest pressure, right? It's about a quarter of an atmosphere of excess pressure, right? 2.7 times 10 to the 4 pascals. So let's just calculate, given this small additional pressure, how high, is the liquid going to go above the level of the solution? Anybody want to guess? A centimeter, 10 centimeters, 100 centimeters, even order of magnitude. Who guesses 1 centimeter? You got 3 choices, 1, 10, and 100, and you have to make 1. Who guesses 1 centimeter? Who guesses 10 centimeters? Who guesses 100 centimeters? Okay. Now, fortunately, we don't do problem sets or other scientific problems by popular vote. rather we just solve them whenever possible. So what's the height of a column of solution? Well, that pi, remember, that's equal to rho times g times h, right? And we know pi now. So h is pi over rho times g. So it's 2.7 times 10 to the 4 pascals over rho. That's 0.995 grams per centimeters cubed times 1 kilogram over 1,000 grams times 100 centimeters per meter cubed. I'm just getting this into units that will give me, that will be in meters, times 9.8 meters per second squared. And when I multiply all that out, it's 2.8 meters. Yeah, so that, puny little pressure, right, ends up being meters high, right, taller than any of us by far, right? Right, so, it's up to there. Right. And that's actually pretty typical. And what that means is it actually makes osmotic pressure a very, very sensitive measurement method, right? If you want to determine a molecular weight, right, for example, right? Because it's so high, that means, and of course you can measure that height pretty accurately, certainly within about a millimeter, right? And so even relatively modest concentrations, it's still easy to see the effect and measure the impact and use that to calculate the properties of the solute. Okay, any questions? All right.